Before we go through some practical examples, let us one more time investigate what kind of real-life phenomena Nassim Taleb talks about in his book The Black Swan. Here we have some examples of random variables that bend the power law distribution. And of course, these examples, Table 2 and Table 3, are taken also from his book, The Black Swan. So we see here in Table 2, for instance, the frequency of use of words has a power law exponent or approximate power law exponent of 1.2. And on Table 3, it gives us basically the implication. So this is basically how power law functions or Pareto distributions are characterized, that a small fraction of the largest observations correspond or make a huge contribution or have a huge contribution of the overall cumulative observation amount. So as we see here, 1.2, the exponent of 1.2, what does that mean? It means that the top 1% of the largest observations make out 47% of the total, and 20% of the largest observation make out 76% of the total. So as we move on here, we have also number or hits on websites, which bends a power law function with an exponent corresponding to 1.4. We have here number of books sold in the US, power law, or an exponent of 1.5. What does that mean? Then we can look again on table 3. It means that the top 1% of the largest observations, so the most sold books, they contribute to, or they make out 22% of the cumulative books sold. Whereas 20% of the books that are mostly sold, they make out 58% of the cumulative total books sold. So we can go down, and here are many examples of random variables that follow a power law distribution as opposed to a mediocristan style normal distribution. So in what follows, we will now go through a recent example, and I will have a data set that is related to cyber attacks, Bitcoin hackings. So we have heard about that quite often in the news. That from time to time some Bitcoins get stolen. So I will show you now here a data series of some Bitcoin hackings. Let's upload this data series into our program Matlab, which is here. So we go on import desktop, and here is the data series is entitled Losses Cyber Attacks. So we upload this data series into our program, we click here the matrix button, and then we have to import everything, putting this wizard. Now it's in the system. As we see here, it's now here in the workspace. Now we can rename it. Let's rename this variable as x. All right. Now we can plot x in order to see how is the distribution, how does it look like. This is basically then how it looks like. So we have here obviously 53 observations, and the largest observation is more than $400 million in one cyber attack. But obviously most of the cyber attacks, they steal only a small amount of Bitcoin. This is what we see here. So now we want to estimate our 53 observations of Bitcoin hackings or cyber attacks. We assume that they bend a power law process. So we want to get the parameters alpha hat, want to estimate the parameters alpha hat and the minimum value x minimum for this data series. So we know we're using the maximum likelihood estimation. Yeah. We want to get the alpha hat and the corresponding minimum value x minimum. So how do we proceed? Yeah, first of all, we define the length of our data series, which is capital T. First, then we denote a new variable coded as x1, and this is the sorted variable. By default, Matlab sorts the variables in an increasing order. So the first element in our sorted vector x1 is then the lowest observation. So let's check that we can copy this to lines directly into Matlab, see what happens. This happens, and if you now go on our x1 vector, which is in the workspace, we see it starts with the lowest observation here, which is $5,000 US. Yeah. So let's continue here. So we define, I told you earlier on the whiteboard that we do the maximum likelihood estimation. So we do it for until a certain observation, and if our x vector, yeah, we have now our x1 vector, yeah, yeah, and we start with the first observation, which is our lowest value. Here's the lowest observation, which is 5,000 in this current example, and the last observation is 400. It was 400 million US dollar, right? So we do the maximum likelihood estimation until the observation capital T1. Yeah. So we stop here. Yeah. So the last 5 observations, yeah, we skip in our estimation procedure. Yeah, because obviously we need some degrees of freedom, yeah, in order to have a proper estimation. So we want that at least 5 observations spend the power law process. Yeah. So let's see how we then proceed. So this is what that's basically why we have to define this capital T1. Yeah, it gives us basically until which observation we estimate our alpha hats. Yeah. So then we define a matrix. It's called results, zeros. It has, of course, the dimension t minus 5 in our case. So if t is 53 and 5 we do not take into account, then our results matrices stores 48 alphas and 48 corresponding x minimum values. Yeah? This is what we for why we need this, or for why we define this result matrix of zeros. Now we have 2 columns, and the length is 48. Yeah. So then, obviously, what we do is we do something form a for loop, and the for loop goes from 1 until 48. Yeah? We know capital T is 53. We skip 5 observations, so our for loop goes from 1 until 48. So, and in each iteration, we estimate the corresponding maximum likelihood estimator alpha hat for our data series. Yeah. So first of all, this is what we see here. So we define x2. Yeah. And obviously this changes in every loop. So in the first loop, it should start at t is 1 until capital T. So what does it mean? So it means, okay, we start here, we take the first observation, and we use the whole data vector until capital T. Yeah. So in the first iteration, we deal with 53 observations. what happens then? Okay, we define the minimum value. So what's in this first iteration? What's the corresponding minimum value? Well, it's the first observation, our x2 vector, and we know in our x2 vector we have the lowest in the first iteration. If small t is 1, we have the lowest observation here, which is 5,000. Yeah. So our minimum value, and this is what we store in the results matrix. Yeah. So our first element that we store is 5,000, and then we want to have in the second column the corresponding alpha hat estimate for that value. Okay. So now we define the length. We say, okay, capital T2 is the current length of that vector that we investigate, and this is obviously here. This is obviously the whole. It's 53 observations, right? So what happens then? We define we define a vector of zeros where we store the values for compounding the maximum likelihood estimator. So you remember from our lecture notes, so that the alpha is defined, the alpha hat is defined as 1 plus n, and we have the sum from I is 1 to n from xi divided by the minimum value x min, if I'm not mistaken. Yes, so this is the logarithm, of course. We have to take the log, the natural logarithm of that expression. Yeah, and this is then what we sum up. So we have to divide every observation here, yeah, by this 5,000, which is the current minimum value. Yeah, take the logarithm and sum up everything. Yeah, for every element, we have to sum it up. So this is what happens here. That's why this is what we store in our x3 vector. Yeah, we store the logarithm of take each element divided by the minimum value, the current minimum value. Yeah, and store it in this x3 vector. So what we have to take then is we have obviously to take the sum of this x3 vector where we have stored all these elements. And this is what happens then here in this line, in line 34. So now we have to have 1 plus the current length of our x2 vector, which is our n here in this formula, and we have defined it as capital T2, and we have to divide it by the sum of our x3 vector, and the x3 vector, we know what we have stored the corresponding elements here. So this is what we have to do. We have to divide the current length of this x2 vector by the sum of the x3 vector, and this is what happens here. Yeah? And then we store the corresponding alpha, the maximum likelihood estimate for the corresponding minimum value of the x in our result matrix. Yeah? So here in the first iteration, we have the first maximum likelihood estimate for the alpha. So then, what we do then is then obviously in the code, the loop, and here in the line 14, we go to the second iteration. Yeah, then obviously we take the next guy here in our sorted x1 vector is then our new x minimum. Yeah, that's our new x minimum. In this iteration, we store this corresponding value in our result matrix. That's the second guy. Yeah. What happens then? Obviously, the length of that of our new x2 vector has now one less observation. It's 52 observations then, right? Because it starts now here at the second place. And again, we take the observations until capital T. Yeah. So then we do the same thing again for this new vector, yeah, but with one observation less in the sample. So then again we compound the maximum likelihood estimator, and obviously because now our capital T2 is now 52 and not 53, so this guy here is also then lower. Yeah? Our new n is then obviously 52 in the second run. Yeah? And here the sum goes then from I is 2, because we start at the second position. Yeah? So that's basically how we would translate this formula iteratively, yeah, in this process of getting the maximum likelihood estimation. So this is what happens, and as you see, yeah, so we have here then some numbers. We get the second estimate for the alpha hat 2, and what you see is obviously, so we do this, yeah, we have obviously in each iteration less and less observations here, and also here in the sum, yeah. So we get less and less observations here, and we stop when we arrive here. Yeah? That's our last x minimum value. Yeah? This is the last element that will be stored here in our result matrix, and it is the last element for what we compound our alpha hat. Yeah? This is basically the idea how one would proceed. Well, again, what comes out? So we get obviously we get a result matrix where we have in the first column the x minimum values, and we have the corresponding point estimates for the maximum likelihood estimator of our alpha hat. And what we can do then is let's just run this code and see what we will get out. Yeah? So let's copy everything here, and of course I will put this into Moodle so that you can use it for your own purpose. Then paste it into the command window. Voila, that's it. Now you see here in the workspace we have now everything stored here. If we now go to on results, yeah, we can copy these two column vectors, and we can open an Excel file and paste it into the Excel file in order to have a closer look on what's happening here. So again, what we see here is, let's insert here a row, and here we have the corresponding x minimum values, and here have the corresponding alpha in the second column, right? So what we can do then is, what we see already here is, if we screen through the observations, yeah, again, remember now we have 48, yeah, 48 observations of our point estimator alpha, and all of them are below 2. What does that mean? Let's take this away. Now we have to remember what we have been talking about, what we have derived here on the whiteboard. So obviously our the first central moment, which is the mean, or the expectation of that power law process, is only defined if the alpha is larger than 2. So the first moment, the expectation of x only exists given that alpha is larger than 2. Yeah? So our power law exponent, as we see here, irrespective which minimum value for x we consider, it's always smaller than 2. Yeah, this is bad news. So let's plot this. Let's take these two data series, and here in X we can go on insert and take this chart here, yeah, this scatter chart, and this is what comes out. Yeah? We have here on the y-axis our estimated alpha hat for the power law exponent, and we have here on the x-axis the corresponding x minimum value. Yeah? And what we see here is we will probably assume that the corresponding value for the alpha is around 1.6. right? So this is basically what we would see here, because here at 1.6 it becomes stable. Yeah, here in the beginning, obviously it increases, and then it becomes stable around 1.6. Of course, we don't have so much observations here, but this is basically what comes out. And if we can test it, we have not talked about it yet, but of course we can also test how good is the data fit, and what we'll see is then obviously that the optimal value is around 1.62. So 1.62 is smaller than 2. It means this process doesn't have a mean. Yeah, it's a very wild process which doesn't have a mean. So obviously, one Bitcoin hacking, thieves they stole 5% of the whole Bitcoin supply in one cyber attack. Yeah. So if this distribution of hackings doesn't have a mean, it means that basically it could be that they hack everything of Bitcoin, at least theoretically. Yeah. Even though the probability is obviously this is a very low probability event, but obviously this means everything is possible. Yeah. This means if the distribution doesn't have a mean. So there are obviously other things, other methods, extreme value. Then we have to go to the extreme value theory, and Nassim Taleb has very interesting research about this. And there's one paper that I could recommend. It's about this COVID-19 research on the risk of contagious disease, tail risk of contagious disease, published in Nature Physics. So you might consult that paper if you want to know how to deal with this kind of distributions that don't have a mean. So my current working paper, I'm working on a new study right now, which is obviously entitled On the Tail Risk of Cyber Attacks in the Bitcoin Market. So what I do is basically I apply a similar approach than Nassim Taleb in his paper, but I'm using Bitcoin hackings as the variable of interest, yeah, and the results are very, very interesting. Yeah, so this is now one way how to deal with it. This is how we get the maximum likelihood estimator, and another thing that is important to know, and again, we don't have a mean, yeah? We don't have a variance. If we don't have a mean, we don't have a variance, obviously. So any higher moment does not exist either. So that's important to bear in mind. So we have also talked about what is necessary for the second moment to exist. So the expectation of the variance, the expectation of x squared, it only exists if alpha is larger than 3. The kurtosis, which is the fourth moment, the expectation of x to the power of 4, it only exists if alpha is larger than 5. Yeah, and you can see the kth moment, the expectation of x to the power of capital K, it only exists if alpha is larger than k plus 1. Yeah, so this is very important to bear in mind when dealing with these kinds of distributions. So obviously, if you have this kind of distribution as cyber attacks, it doesn't make sense to argue with a sample mean, okay? Because it doesn't because the mean of the underlying distribution doesn't exist. Even though we have a finite sample, a sample is always finite, yeah? And we have always a sample mean, yeah? But the sample mean has no information about the actual expected value of the distribution because it doesn't exist. Okay, so this is very, very important to bear in mind, because this is where things go wrong in social science all the time. So next, let's take another example. Let's take as another example Bitcoin volatility. It's again an example from, let's take this away. We take again an example from finance. because obviously my background is in finance, but this is obviously for any other social science as well. We have to bear in mind what John Peterson, who is professor of psychology, he told us that the Pareto distribution, which is same as a power law, this is just another way to express it. Power law is the same like Pareto distribution, and there are of course slightly different, let's say, notations how you define this distribution, but all of them measure the same thing basically. He argued in his lecture that the Paretian distribution, respectively a power law, is the inevitable solution of a trading game. Yeah. So obviously, Nassim Taleb is right when arguing that power law should be the norm. Yeah, because what is economics about? Economics is about trade. Okay, it's about trading. It's about trade, irrespective if we consider like financial markets, if we consider just like stocks or which is obviously also all about trading, but also any other market. Yeah, if countries deal with its export, import, all of this is trading. So economic variables, they have to do with trading. Okay, so Nassim Taleb also argues, obviously, if you remember, that everything is a man-made phenomena. Man-made phenomena. They typically are not normally distributed, but they tend to be distributed as power laws. So that's why this class of distributions is very, very important. Let's delete this, what we have done so far, from our workspace. Let's delete it here, and let's upload a new vector, import data, desktop, and let's take the Bitcoin volatility. Yeah, we have now much more observations. Yeah, we're dealing with daily observations, and we're using a high-low closing price as corresponding elements here, and compound the realized volatilities for the daily using daily data. Yeah? BTC volatility, let's rename it as our X variable, and we use our code that you find in Moodle that I've written by myself, and put it in here, paste it into the command window of Matlab. So again, you just have to wait a second. What we get out is here the results. Again, let's copy that into a Excel file in order to have a more view on how it looks like. Put it in here. So obviously there are some missing observations. We can just delete it. Let's delete it and shift the cells up. So we know that in the first column there is the X minimum value, right, which is the corresponding realized volatility, and here we have the exponent, the alpha. Yeah. So let's plot it again. We have now 2,700 observations, which is obviously much better in order to come to a conclusion. Yeah. Here we can obviously really do good analysis on this using this scatter plot, and this is what comes out. And if you study, if we have, it's also on the reading list, the paper from Clauset et al. What deals with power laws, and you will also encounter much more different processes and where they run this kind of methodology. So what we see here is again the settle point. You see here it's somewhere between 3.4 and 3.5. Yeah, this is basically here is the optimum. So you would we have obviously a volatility that is around 1.5. Yeah, around 1.5 as you see here, and the corresponding power law exponent is around 3.45, 3.46, 3.47. So obviously we have also standard deviation. Yeah, so if we have estimated the alpha, let's take this away. We need some space here. But remember the moments. How are the moments defined? Because there might be a question in the exam about this issue. So we also need to know how the corresponding point estimates are distributed. So we have a t-statistic for the alpha. And let's have a look at the paper from Clauset. So this is the paper from Aaron Clauset. Yeah, what I would like you to go through. And if we go through this paper, yeah, you see in my paper, obviously, I follow the notation from this paper here. I told you there are different notations how to define power law processes, yeah? And I follow his notation basically, or the author's notation. Yeah. So here, basically, here as you see, here are different ways how to express power law processes, discrete and continuous, and so on and so forth. So what we do is we follow the standard process here. Let's just scroll down here. This is our point estimator, yeah, as they reported in the paper. Yeah, it's the same thing that what we have done here in our derivation. So the standard deviation, what we see here we see the standard deviation, or the variance. So if we have the estimated alpha, yeah, we can get the corresponding standard deviation, which is sigma, yeah, and it's defined as we see here in this paper. It's the estimate of the alpha. It's alpha hat minus 1 divided by the square root of n. And if you want to be very precise, we have to add here, obviously, the 1 over n. And of course, this term here, it disappears if n is very large. Yeah? So if we have 10,000 observations, obviously this term disappears. What only matters then is this guy here. So if we want to have a confidence interval, yeah, for that point estimator, so what we can do is, so we can say, okay, let's have obviously this is normally distributed, okay, the alpha is normally distributed, it's a maximum likelihood estimator. So if you want to have the confidence interval in order to run a t-test, so what we can do is, okay, we can say our alpha is, so we can take 2 or 1.96 times this sigma, and minus 1.96 times this sigma here. This would be a confidence interval covering 95%. Yeah. So our real alpha is then somewhere in this confidence interval of minus 1.96 times this sigma and plus 1.96 times this sigma. Now, this is also very important to bear in mind. So obviously the t-statistic of our alpha hat is then simply the alpha hat, yeah, divided by our sigma, which is here. So that's the t-statistic basically. This is also very important to bear in mind. So again, let's go back to our analysis here. As we see here from our graph, so according to the paper from Clauset et al., so it's basically the saddle point here would be the optimum for the alpha hat. So there are also, as I told you already, there are also other possibilities to do it in a more analytical manner. So this is what the authors also propose to do. So in order to do that, in order to choose the analytical or more analytical approach, yeah, we have to do simulation studies. So let's talk about once again about simulations. So you obviously know how to do the simulation. We have been discussing this in our earlier lecture. So we need some pencils here. So let's say we have, to keep things simple, let's say we have 10 observations. Yeah? 10 observations that bend the power law. Yeah? So we know that the probability, so we can formulate an empirical probability function or empirical cumulative density function. Yeah? And we know that from the x minimum value, we have, and we have, let's say, 10 observations, so t is 10, yeah? So we know that our x minimum value, the integral from our x minimum value to infinity is 1, so it's t over t, okay? It's t over t observations. We know that the second lowest value, let's call it x, if this is x minimum, let's call it x2. If this is our first value, then this is our second value. So we have the how much of the probability is on the right-hand side. It's obviously our capital T minus 1 over t. If you take the next guy, it's capital T minus 2 over t. And so on. And the last guy here has obviously 1 over t as the corresponding probability mass. If you take the cumulative probability on the right-hand side of the distribution. So that's our empirical cumulative density function, right? So our empirical cumulative density function. Let's abbreviate it as ECDF. So what we can do then is we can compare, that's our empirical density function, and we can compare it with the theoretical by simulation. So let's say you know how the simulation works. You have the I gave you the formula. You can run a Matlab code and do 10,000 or 100,000 simulations. You get 100,000 observations, random observations of that power law process. So what you can do is, let's denote this vector as the simulated vector as x. Now in green, obviously. So it is a vector that has a length of, let's say we have 100,000 simulations. What we do is we can sort this vector from smallest to highest observations, and then we can compare. We can plug in each of our values of the sample, having the estimated alpha and the x minimum. Again, we can simulate the theoretical density function, using our simulation method. Okay, so we have then realizations of the simulated vector of that corresponding theoretical distribution. We sort it from the lowest to the highest observation, like it is here the case in our vector of the empirical function, and we compound the theoretical density function, So we compound the corresponding TCDF, the theoretical cumulative density function, So we take the first guy here, the x minimum, and we say, okay, obviously this must be 1. This is always 1 per definition, because it's the minimum value. So everything that is the minimum value, the integral from the minimum to infinity is always 1. Okay, so that's not the problem. So the next guy here, we know from the empirical cumulative density function, it's t minus 1. So if you have 10 observations, it's 10 minus 1 is 9, 9 over 10. It's 0.9. And now we count all realizations here in our theoretical, in our vector of theoretical realizations. We count all the numbers that exceed this value here in the theoretical vector of observations. And it could be that we have, let's say, here we have 0.9, and it could be that, let's say, 88%, yeah, 88% are above that value. Let's say x2 is here, yeah, and 88%, 0.88, are exceeding this value of our observation. So it could be that the theoretical cumulative density function has for the second observation gives us a value of 0.88, which is the theoretical value, and if our empirical value is 0.9, the difference is the so-called Kolmogorov-Smirnov distance, or it's abbreviated as d. Yeah? D is the absolute amount of that distance, so it's 0.9 minus 0.88, and that's obviously 0.02. Yeah, and it's the absolute amount. So if this guy here would be the other way around, if this would be 0.88 and this would be 0.89, it's anyways the same distance. So it's an absolute measure in absolute terms. And we can do the same thing for all the other observations here as well. Yeah, we compare the corresponding value of the empirical cumulative density function with what should be the value according to the theoretical cumulative density function. Yeah, and the distance between empirical value and theoretical value is a distance. Yeah? So obviously, yeah, if we plot, let's say, theoretical t against E, yeah, if everything ends up on a straight line, the fit would be perfect. Yeah? But usually what you see is that it doesn't end up like this. It looks a little bit like this. Yeah? So we have obviously always a little bit like deviations from the value that we have in the empirical sample versus what we should have if this would be a perfect fit. Yeah? So this is a method how we can investigate this the data fit. Yeah? What you can then do is, okay, you can say, okay, the maximum here, the maximum deviation. Yeah? Let's take the maximum deviation d, yeah? Which is the maximum deviation, and what we can do then is we can simulate thousands of theoretical functions using these input values here, yeah, and we can estimate the maximum likelihood estimator for each of these theoretical functions. They're doing the same thing all over again, yeah, and what we get is then we get simulated differences d, yeah, and what we do then is we can count the number. Because under the null hypothesis, we know that these we know that it's under the null hypothesis has exactly this distribution, so we can count the numbers of times where the simulated exceeds the value d, yeah, that we have in our real life example, yeah. So, and what we know is if this value here, if this p value here is larger than 5%, so if more than 5%, if more than 5% of the simulated using the synthetic data of the simulated Ds are on the right hand side of that simulated distribution, yeah, if more than 5% exceed this value d, red d, then our null hypothesis that this power law model is right cannot be rejected. So that's basically, this would be the more analytical test, which is also discussed in this paper from Aaron Clauset et al. I will probably not ask this in the exam, yeah, but you should read it in the paper in order to get familiar with that. Because obviously there's always some uncertainty in the process, so we are not 100% sure that the corresponding estimates are really like correct. Obviously, there are many different distributions possible. The only thing that we know is if we have a look at the data, what we can be sure about is that the process is not thin-tailed. If a process is fat-tailed, then it could be a power law process, but we are not 100% sure about the parameters. So it's all about estimation. So there's an uncertainty in the estimation. Obviously here, if we have this process here, it's pretty clear. We have a lot of observations, and we see clearly that this looks basically exactly like figure 3 in Aaron Clauset et al. Paper. It looks basically like a simulated process. So there's not much doubt about the accuracy of our power law exponent. It must be around 3.5. And then we have also this here, obviously we can estimate the t statistic, so we can give a confidence interval, and it will be about 3.45, 3.55, okay, with a 95% probability. But if you have a smaller sample, this kind of analytical test becomes more important. Okay, this is what we have to bear in mind. So using these simulated data, we can easily tell, okay, how much observations are above a certain threshold. So we remember now, this is now the last thing that we would like to discuss from when we discussed the book The Black Swan. We remember that Taleb argues that this alpha, it captures the low probability event, which is obviously true, and the theoretical how we can basically interpret the alpha exponent. So obviously the exponent captures the low probability event, and the lower the alpha, the larger is the impact of the tail event, of the outlier. So in his book on page 265, Black Swan 265 and 264, he's talking about, he gives examples, and we have talked about it also in the lecture when we went through this book. Now, in his notation, what is his alpha? If he talks about the alpha of 1, it's in our notation alpha of 2, because we have a different definition of a power law process. Okay, so this is what we have to be. We follow the paper from Aaron Clauset, and Nassim Taleb has a different, follows a different notation in his book, and also in his scientific papers, by the way. So when he talks about alpha of 1, in our case, it's alpha of 2. So let's say on 50 days, the return, we model the return distribution of an asset using power law process. So let's say on 50 days, the returns, we know that on 50 days, the returns are above 4%. Okay? So on how many days are the returns above 8%? So using his the formula in his book, from his book, it is obviously 50 times 8 over 4. Now we have the exponent is negative, so it's to the power of minus 3.5. Let's say, as we see in Bitcoin, in our case, Bitcoin 3.5. Let's say we have an exponent that's estimated at 3.5. Yeah. So we have to subtract now minus 1. Yeah. That's now the important thing. So the corresponding number would be on 8.84 days. Yeah, we would have returns that are above 8%. Yeah, this is one example, one important example how to interpret the alpha. Yeah, in his book, he neglects this. Why? Again, because he's using a different definition. Yeah? But if we want to calculate it for our model that we used in this lecture, yeah, we have to interpret it. We have to interpret it like this. If we have estimated this guy, it's our alpha, yeah, so our estimated alpha. So if we want to basically interpret our polar exponent, yeah, we have to subtract -1 here. Okay, that's important to know. Yeah, that's basically what you would like to talk about here in this lecture. So again, we have to be aware of that. Yeah, in this case, let's go back to our Bitcoin example here, the Bitcoin volatility. Yeah, we have here the volatility as input process. So our alpha is 3.5, which means the mean exists. Yeah, because it's larger than 2, and the variance exists as well, because 3.5 is larger than 3. Okay, so in this case, we would conclude that Bitcoin volatility has a mean, it converges, and because the variance of that volatility exists as well, so the variance, the volatility is stable. This is what we would conclude based upon that data. Thank you very much for your attention.